One number is about to break your brain. 1,000 kilometers per second. That's roughly 2.2 million miles per hour, fast enough to cross the entire United States in about 4 seconds. Now imagine our entire planet slamming into Uranus at that speed. Not a gentle nudge, not a grazing pass, a direct hit at a velocity almost nothing in our solar system naturally reaches. What actually happens in that collision isn't science fiction. It's a physics problem we can actually solve using real numbers, real masses, and real energy calculations. And the answer is stranger and more violent than almost anyone expects. Welcome back to Reality Vault. If you're new here, this is the channel where we take wild what-if questions and run the actual numbers instead of guessing. If that's your kind of mystery, hit subscribe now, because by the end of this video, you'll understand exactly what surviving would even mean in a collision like this, and the honest answer might surprise you. To work through this, we're following 3 people who approach the same impossible question from 3 completely different angles. There's Dr. Eleanor Voss, 42, an astrophysicist based in Berlin who specializes in planetary collision modeling. There's Jamal, 31, a science communicator from Lagos who spends his days translating dense research papers into content people can actually understand. And there's Grace, 58, a retired NASA propulsion engineer from Houston who spent decades thinking about velocities most people never have to consider. Before we run the numbers, let's be completely upfront about something important. A collision at 1,000 kilometers per second is not something we expect to happen in real life. Planets in our solar system move relative to each other at speeds of maybe 10 to 70 kilometers per second during close encounters. This scenario is roughly 20 to 100 times faster than anything gravity alone would realistically produce between Earth and Uranus. This is a hypothetical thought experiment, not a prediction. Everything that follows is a what-if, built on real physics, but applied to an imaginary setup. The contenders. Elena starts where she always starts. Know your subject before you destroy it. Earth, fact. Our planet has a mass of about 5.97 times 10 to the 24th kilograms, and a radius of roughly 6,371 kilometers. It's a rocky planet with a solid iron core, a mantle of dense rock, and a thin crust we happen to be standing on right now. Uranus, fact. It's what astronomers call an ice giant, not a gas giant like Jupiter, a distinction most people online get wrong constantly, and Jamal makes a point of correcting it early. Uranus's interior isn't mostly hydrogen and helium gas the way Jupiter's is. It's a dense, slushy mix of water, ammonia, and methane ices surrounding a smaller, rocky core, all wrapped in a thick atmosphere of hydrogen and helium. Uranus has a mass about 14.5 times that of Earth and a radius about 4 times larger. It also famously rotates almost completely on its side, tilted 98 degrees, likely, theory not confirmed fact, the result of a massive collision billions of years ago. That detail matters later, because it means Uranus already has a violent history. Jamal jumps in with the myth most people believe walking into this video, that because Uranus is mostly gas and ice, Earth would simply sink in or get absorbed with minimal drama, like a stone dropped into a pond. Here's where the mystery becomes even stranger. That's not remotely what the math shows, running the numbers. Grace, the engineer in the group, insists on doing this the boring, correct way, with actual kinetic energy math, because emotional guessing gets planetary collisions wrong every time. The formula for kinetic energy is simple. 1/2 times mass times velocity squared. Kinetic energy, the energy an object has because it's moving, is exactly what determines how destructive an impact will be, far more than the size of the objects involved. Earth's mass, again, is about 5.97 times 10 to the 24th kilograms. At 1,000 kilometers per second, That's 1 million meters per second. Squaring that velocity and multiplying by half Earth's mass produces a kinetic energy figure of roughly 3 times 10 to the 36th joules. That number means almost nothing on its own, so Elena puts it in context. The asteroid impact, widely believed to have ended the age of dinosaurs 66 million years ago, released an estimated energy of around 4 times 10 to the 23rd joules. A hypothetical Earth-Uranus collision would release roughly 10 trillion times more energy than that extinction-level asteroid impact. This single clue changed everything about how we need to picture this collision. We're not talking about damage. We're talking about annihilation on a scale almost impossible to visualize. Grace pushes the comparison even further. Earth's own gravitational binding energy, the amount of energy needed to completely tear the planet apart and disperse it into space, overcoming its own gravity, is estimated at around 2 times 10 to the 32nd joules. The kinetic energy of our hypothetical collision is roughly 10,000 times greater than the energy needed to unbind the entire planet. That's a fact-based conclusion drawn directly from established physics, not speculation. At 1,000 kilometers per second, Earth wouldn't just crash into Uranus. It would be shattered and vaporized well before whatever remained finished penetrating the ice giant's outer layers. What would actually happen? Jamal wants the cinematic version, so Elena walks him through it step by step. This is where fact starts blending carefully into theory. Fact: at that velocity, the shock wave generated on impact would travel through Earth faster than sound, could carry any warning through the planet's own structure. Within a fraction of a second, the compression alone would generate temperatures theoretical models suggest could exceed those found in the sun's outer layers, briefly turning solid rock and iron into superheated plasma. Theory, and this is where serious astrophysical modeling comes in. Researchers who study high-velocity planetary asteroid impacts using computer simulations suggest that at these energy levels, a collision doesn't behave like two solid objects crashing together at all. It behaves more like an explosion. Much of Earth's mass would likely vaporize outward in an expanding cloud of superheated debris, rather than staying intact as a single moving object punching through Uranus. Uranus wouldn't walk away clean either. Grace's engineering instinct kicks in here. Even though Uranus is over 14 times more massive than Earth, an impact delivering energy in the range we calculated would still disrupt its outer atmospheric layers dramatically, likely triggering enormous storms, and depending on the exact impact angle, potentially disturbing its ring system and the orbits of its inner moons. Whether the impact would be enough to meaningfully affect Uranus's deep interior or overall structure remains genuinely uncertain. This is a case where scientists are honest, that the answer depends heavily on impact angle, exact composition layering, factors current models can only estimate, not calculate with certainty. Correcting the big myth. Before we get to who survives, Jamal wants to correct the myth that brought most viewers to this video in the first place. The idea that this kind of collision could realistically happen from a stray asteroid, a rogue planet, or planetary alignment gone wrong, as some viral posts have claimed. Fact: nothing currently tracked in our solar system moves anywhere near 1,000 kilometers per second relative to Earth or Uranus. Even long-period comets, some of the fastest natural objects we observe, typically reach speeds of a few dozen kilometers per second relative to Earth at closest approach. Rogue interstellar objects passing through our solar system, like the famous Visitor, Oumuamua, discovered in 2017, have been measured moving at tens of kilometers per second relative to the Sun, not thousands. Reaching 1,000 kilometers per second would likely require an object falling from an extreme distance under powerful gravitational acceleration, some kind of exotic scenario far outside anything currently observed. This scenario stays firmly in the realm of imagination, and that's exactly why it makes such a good thought experiment. It lets us push real physics to an extreme most real-world collisions never approach. So, who survives? Eleanor, Jamal and Grace all arrive at the same blunt conclusion, even though they got there through different specialties. At 1,000 kilometers per second, survives isn't really the right question, because planet would remain the object it was beforehand. Earth, based on the energy math, would very likely be destroyed outright, vaporized and scattered rather than punching a clean hole through Uranus. Uranus, protected by its far greater mass and its deep atmosphere, would probably remain the more intact of the two, its core surviving in some form, but its atmosphere, rings, and possibly its moon system would face catastrophic disruption in the aftermath. If you had to pick a technical winner, Uranus keeps more of itself intact by sheer mass advantage. But calling anything left standing a survivor honestly stretches the word past its normal meaning, given the scale of destruction on both sides. Grace put it best while double-checking the final numbers. At speeds like this, you're not asking which planet wins. You're asking which pile of debris ends up bigger. So here's the question we'll leave you with. If you could pick any two objects in the solar system to collide in a hypothetical scenario like this one, which matchup would you want us to calculate next? Let us know in the comments. And if there's a cosmic what-if you've always wondered about, tell us. We might build the next investigation around it. If this video blew your mind a little, share it with someone who loves space mysteries and subscribe to Reality Vault so you don't miss the next one. This video is created for educational and entertainment purposes. The information presented is based on publicly available sources, historical records, scientific research, and documented theories. Some topics discussed remain unsolved or debated. Viewers are encouraged to do their own research and consult reliable sources for further information.